Without further ado, I'll hand it over to Matthew.
Awesome. Thank you very much. All right. So, what if I told you that alien life forms were on their way to Earth right at this very moment? We know that they're very different from us. We know that they're super intelligent, and we know that they have superior technology. However, we don't know if they're going to be friendly or hostile. We don't know how their arrival will affect our world, and we don't know exactly when they're going to arrive, but we predict that they're going to be here within the next decade or so. So, what would you do if you found out that all of this were true? Like, how would you prepare yourself, your family, and your business? And how should we prepare our economy, our society, and our world? Well, this alien arrival story, it might sound like science fiction, but I assure you it is absolutely true. However, this alien life form isn't traveling to Earth from some faraway planet. Rather, it's already here, just waiting for someone to put all of the pieces together and wake it from its slumber. The alien life form I'm referring to is artificial general intelligence, and it's likely much closer than you might imagine. So the purpose of this presentation is to learn about artificial general intelligence, where we are today, where we're going, and how we're going to get there. And along the way, we'll be looking at the latest research in the field of artificial intelligence. I want to help you to understand what's coming so that it doesn't take you by surprise when it finally arrives. As an overview of our presentation, first, we'll learn about artificial general intelligence and how it's different from our modern AI. Next, we'll discuss the problems of AI that we've already solved in the past. Then we'll discuss the problems of AI that we're currently solving today. Next, the problems that we need to solve over the next few years. Then the problems that we might have to solve in the future. And finally, we're going to end our journey by defeating the final boss, which I'm going to keep as a surprise until the end. All right, before we begin, though, I think it's important that I at least introduce myself so you know who I am, where I'm from, and why I'm interested in this topic. So I'm Matthew Renze, an AI researcher, consultant, and author. I'm actually originally from Iowa. I now live in Las Vegas. As the owner of Renze Consulting, I've taught over 500,000 software developers and IT professionals. As the president of Renze AI Research, I run a nonprofit organization dedicated to AI research and education. I have my master's degree in artificial intelligence from Johns Hopkins University, and I'm also a Microsoft regional director, a Microsoft MVP in AI, and the author of several successful online courses. And just for fun, I have presented on every continent in the world, including Antarctica. All right, so the road to AGI is going to be a long one, and our journey is going to be difficult. So to make things easier for everyone, we're going to approach this presentation like a hero's journey. With each milestone on our journey, we're going to be picking up the pieces of the AGI, artificial general intelligence puzzle along the way, the fragments of this alien life form that we'll need in order to bring it to life. And you can think of this like Harry Potter collecting the Horcruxes of Voldemort, or if you're old school like me, Simon Belmont collecting Dracula's relics in Castlevania 2. We're going to be traveling through time, collecting the necessary components of artificial general intelligence along the way so that we can use them to defeat the final boss here at the end of our adventure. All right, so we have a long road ahead of us today. Let's get started. First, what is artificial general intelligence? In order to answer this question, we first need to answer the question, what is artificial intelligence? So, what is AI? Well, artificial intelligence is a subfield of computer science that attempts to create machines that act rationally in response to their environment. An AI is a machine that perceives its environment and chooses the actions that maximize the expected likelihood of achieving a goal of some kind. Essentially, it's just a machine that takes data as input and produces the best possible output given what it currently knows. And now, when I say artificial intelligence, many of you will immediately think of modern AI tools like ChatGPT, Amazon Alexa, or Tesla's self-driving car. Now, this is what we call artificial narrow intelligence, or narrow AI. Narrow AI is focused on performing a very narrow set of specific tasks, and this is the type of AI that exists today. On the other hand, many of you may think of sentient robots like R2-D2, Data from Star Trek, or HAL 9000. And this is what we refer to as artificial general intelligence, or general AI. General AI, in theory, can perform a wide variety of general purpose tasks. It's the type of futuristic AI that doesn't currently exist today. And some of you might also think of super intelligent superheroes and supervillains like Vision from the Avengers, Vicky from the movie iRobot, or Skynet from the Terminator movies. And now this is what we refer to as artificial super intelligence, or super AI. A super AI can perform every task that a human can perform, but better than any human. And once again, artificial superintelligence doesn't exist yet either, and we don't know if or when this might come into existence. Now, in this presentation, we're going to work our way from the narrow AI that we have today to the general intelligence that we'll have tomorrow and end up with the superintelligence that we might have in the future. And that brings us back to our original question. What is artificial general intelligence? Well, AGI is a machine that can perform a wide variety of economically valuable tasks better than an average unskilled human worker. Essentially, it's an AI that's as good or better than a human at doing work that humans do every day. However, AGI probably won't be an all or nothing event. It will likely be a gradual transition over the next few years or decades. As a result, AI researchers are now discussing various levels of artificial general intelligence, capabilities of an AI that will emerge over time. And you can think of this like the 5 levels of autonomy in self-driving vehicles, if you're aware of that. So at level 0, we have no generality. This is where the narrow AIs that we have today. And level 1 is emerging AGI, the sparks of artificial general intelligence that we're beginning to see with large language models like GPT-4. Level 2 is what I'm referring to when I say AGI. It's an AI that can do roughly half of all the tasks better than an average person. Level 3 is better than most humans at most tasks. Level 4 is better than almost all humans at almost all tasks. And finally, we would have level 5, artificial superintelligence, a machine that can perform all economically valuable tasks better than any human. And so when is this going to happen? Like, when do we think we're going to achieve AGI and artificial superintelligence? Well, based upon various surveys of AI experts, they predict that we'll achieve artificial superintelligence somewhere between 2040 and 2060, a pretty wide range of potential values. And that would lead us to a prediction of artificial general intelligence somewhere between 2030 and 2050. However, the actual data from AI research now tells a much more optimistic story. These AI systems are achieving human-level performance on complex problem domains at a progressively faster rate each year. And the exponential increase in the number, the size, and the capabilities of AI systems has many AI experts convinced that we're going to achieve artificial general intelligence or possibly even artificial superintelligence before the end of this decade. Ultimately, predicting the future of AI is extremely difficult. Nobody really knows for certain if or when this is going to happen. All right, so our practice time is over. All of our training is complete, and we're ready to begin our adventure. First, let's discuss artificial intelligence of the past, the problems that we've overcome in the last few decades of AI research. Problems like creating artificial brains, teaching machines how to learn, and how to perceive their environment. Now, it might surprise some of you that artificial intelligence has been around for quite some time. In fact, the field of AI dates all the way back to the 1950s. In 1956, a group of computer scientists got together for the first conference on artificial intelligence. And this conference kicked off the first wave of AI research, the symbolic AI era, and gave us the name artificial intelligence. The first wave of AI research led to several early successes in symbolic AI. We had several key advances in state space search or heuristic search, computational logic, and natural language processing. The most important of these advances for the purpose of our journey to artificial general intelligence today was the development of the first neural networks called perceptrons. Simple neural networks consist of a set of input neurons, a set of output neurons, and a hidden layer of neurons in between. The neurons are connected by a set of edges that propagate information from the input to the output of the neural network. Data goes into the input layer, and then prediction of some kind comes out at the other end. The input neurons take a set of numeric values as their input, and the hidden layer performs a bit of math, and then the output layer produces a prediction, represented as a probability that the thing it's seeing is what it believes it is. Now, neural networks allow us to make decisions and predictions similar to organic brains. They essentially allow us to, or provide us with an artificial brain for an AI system. However, there are still several limitations to the early neural networks that we eventually discovered. And the result was that the promise of neural networks quickly faded away. And this in part led to the first AI winter, a period from the mid-1970s to the early 2000s where we saw a significant reduction of funding and interest in AI research. Essentially, the heyday of classic artificial intelligence had ended. Now, after the AI winter, researchers went back to the drawing boards in search of a new path to artificial general intelligence. This era of AI focused largely on how to learn knowledge from data, and we refer to this type of AI as machine learning. The era of machine learning was successful largely because we now had a tremendous amount of data available, significantly more compute power, better algorithms for training AI models, and a more disciplined approach to AI, a data science approach. Essentially, with machine learning, we use existing data and a training algorithm to learn a model of the data. We can then feed new data into that model that is never seen before and make predictions about the new data. A machine learning model is essentially a function, just like we learned about in high school algebra. It's simply a mapping from an input to an output of some kind. And in this case, it takes data as input and produces a prediction as its output. For example, imagine that we wanted to create a function to determine whether a photo contained an image of a cat or not. We want our function to take in an image as input and produce a prediction of either cat or not a cat as its output. So how would we do that? What would we need to do in order to create an AI cat detector? Well, first, we'd need to create a data set that contains a bunch of images of cats and images without cats. We would have a human label each photo, indicating whether the photo contained an image of a cat or not. Next, we would apply a machine learning training algorithm to that data set of images with and without cats so that it could learn what catness is. The algorithm would learn what is different about the pixels in an image with a cat versus the pixels of an image without a cat. The training algorithm would then produce a machine learning model. The model encodes the statistical relationship between the input image and the two categorical output labels of cat versus not a cat. Finally, if we've done everything correctly, we should be able to provide the model with a new image that it's never seen before, and then the model is going to tell us if the image does in fact contain a picture of a cat or not. More specifically, it will tell us the statistical likelihood that the image contains a cat. And now, while it's a vastly oversimplified explanation of machine learning, but it essentially captures the essence of what it is that we're attempting to accomplish. However, machine learning still has several pretty significant limitations. And so many experts thought we were headed towards another AI winter back in the 2000s. All right, so fortunately, several advances in AI led us out of the machine learning era and straight into the deep learning era. The most important of these advances was the deep neural network. A deep neural network is a neural network with more than one hidden layer, and by adding more hidden layers allows the network to model progressively more complex functions. For example, if we want to teach a deep neural network how to detect human faces, first, in the input layer, we would feed it a set of labeled images of human faces so that it could teach it what different faces look like. The first layers of the neural network or deep neural network learn to detect geometric primitives, for example, horizontal lines, vertical lines, diagonal lines, etc. The middle hidden layers learn to detect more complex facial features like eyes, noses, and mouths. The later hidden layers, they learn to detect more general patterns for entire faces. And the output layer learns to detect the most abstract representation of a person, for example, the name of the person being recognized. Each subsequent layer learns to extract more complex features from the preceding layer, and as a result, each additional layer detects more abstract representations than the previous layer. And we can also flip these deep neural networks around conceptually to allow them to generate complex output from abstract input as well. And this is a technique used in generative AI, the technology behind like deep fakes. So deep learning takes us beyond using simple tabular data as input and producing simple tabular data as output. With deep learning, we can use complex data as input and produce complex data as output. This includes text, images, audio, video, and more. Deep learning gives us the ability to perceive, it gives AI the ability to perceive its environment and make predictions about future possible states of the world. However, there are still several limitations to deep neural networks in the deep learning era. So once again, we're going to need a new path forward for AGI. All right, so this is where we're at today. Over the past 70 years, we've seen some amazing progress on the road to AGI. However, like along the way, we've picked up some really important pieces of the puzzle. For example, we now have a brain for AGI using architectures like deep neural networks. We have the ability to learn purely by observing data, and we have perception to sense and perceive the world. So let's put these pieces of AGI that we've collected into our inventory bag and start on the next phase of our journey, AI of today. All right, so next we're going to discuss artificial intelligence of today, the problems that we're overcoming right now on the road to artificial general intelligence. Problems like attention, understanding, and agency. In 2017, Google published a paper titled "Attention is All You Need." In this paper, they introduced the groundbreaking idea of self-attention. Attention helps a deep learning model focus on the most relevant parts of the input data. Attention was a major breakthrough at the time, and it led to a new architecture for deep neural networks called the transformer. And now transformers, these are the foundation of large language models like ChatGPT and Google's Gemini. They marked a significant leap forward in generative AI. Now, this is my super oversimplified explanation of how transformers and self-attention works. In this example, our goal is going to be to use the input words on the screen to predict the next most likely word. First, we convert the input text into a sequence of tokens. Tokens are typically either whole words or subword like prefixes and suffixes. Next, we convert each token into a numeric vector representing each token's position in something we call an embedding space. In an embedding space, words that are similar in their meanings are close together, like cat and kitten, while dissimilar words are further apart, like the difference between cat and dog. However, in a transformer, the embedding space is more than 2 dimensions. Typically, we're talking about hundreds or even thousands of dimensions. Now, then we apply the self-attention mechanism to the sequence of vectors for each token. Attention measures how important every word in the sentence is to every other word. For example, small and fluffy are strongly associated or attend to the word cat, while big and brown attend to whatever word's going to come next in this sentence. Next, we perform a bunch of math across the multiple layers of these vectors representing each token. The math uses the importance of these modifiers to essentially nudge words where they belong in this hyperdimensional embedding space. For example, small and fluffy are going to modify the word cat and nudge it closer to the word kitten in this embedding space. Then we use the position of all the tokens in the embedding space to predict the next most likely token in the sequence. You can think of it like a jigsaw puzzle. So based on all of the pieces that we currently have, or tokens, we predict which piece will fit next by considering the shapes and colors of all of the neighboring pieces. However, there are typically multiple possible next tokens. So we either need to choose the most probable one, or we randomly select a token from the top most likely options. Then we append that new token to the end of the text. And then finally, we feed that sentence with its new token back into the transformer's input, and it predicts the next token as output. And we repeat this process so on until it encounters a stop token like the period there. We call this process of using the previously generated tokens to generate the next most likely token, something called auto-regression. Now, in addition to self-attention, like we just saw, there's also several other types of attention. For example, we have cross-attention, where we determine the importance of each input token to every output token, and visual attention, where we determine which pixels in an image are most important to making that prediction. However, there are still several limitations with transformers and their attention mechanisms. For example, they tend to hallucinate, they make up statistically plausible yet entirely false information, and they are very confident in doing so. And interestingly, though, the larger we scale these models, the better they get. Now, most experts thought that these scaling gains were only going to last a few years. However, even based on the latest research, there still appears to be no end in sight. Now, when we walk outside, we have a general understanding of the world around us. We understand spatial relationships, temporal cause and effect, and basic physics of the world. We have this natural understanding of our environment because we've observed how it behaves over many years. However, AI systems don't naturally have this ability. They don't experience the world the same way that we do. So they don't understand concepts like spatial relationships, temporal cause and effect, or the physics of the real world. To solve this problem, we need to create something inside of the AI known as a world model. A world model is an internal representation of the external world that allows the AI to understand, predict, and reason about its environment in a coherent manner. So the natural question you might have is, does an AI like ChatGPT possess a world model? And the answer is maybe. We're not entirely sure. So many experts think that LLMs like ChatGPT are just what we call stochastic parrots. They're simply mindlessly repeating the next most likely token given the previous tokens. And that is definitely the case with the first few generations of these transformer-based language models. However, when you scale these models up to billions of parameters using trillions of training samples, it looks like they begin to develop a rudimentary world model. But keep in mind, this is a model of the world solely as described in text. For example, when an LLM learns to predict the words in the phrase, he shoots, he scores, it's learning a lot more than just the probability of the next most likely token inside of its weights. It's learning basic concepts, relationships, analogies, and more. It's learning that throwing a basketball into the hoop leads to scoring a point. So when it encounters a person with another kind of ball-like object, like a crumpled up piece of paper, throwing it into a different kind of basket-like object, like a trash can, it understands that the person desires to get the ball of paper into the trash can to score an imaginary point. And now this is very different from stochastic parroting. A purely text-based world model allows an AI to learn a very primitive types of spatial relationships, temporal cause and effect, and physics of the real world. It allows the system to use the current state of the world, as described in text, to make predictions about future states of the world, also as described in text. The emergence of world models in LLMs has led to what we refer to as emergent properties, these behaviors that simply don't exist in smaller models, but then suddenly appear out of nowhere as we scale these models to larger sizes. So out of this primitive world model, other emergent properties have started to develop. For example, chain of thought reasoning, the ability to think step by step through problems. Sense of humor, the ability to understand and create original jokes from scratch, and some of which are actually kind of funny. Theory of mind, the ability to predict what a person knows or feels based on observation and context alone. And creativity, the ability to create original stories, poems, songs, pictures, and videos from scratch. And now these behaviors seem kind of unlikely if the LLM is just memorizing text and spitting back the next most probable word. And now I'm not saying that large language models understand the world just yet. All I'm saying is that it appears that they're beginning to build a rudimentary world model. All right, so agency is the ability to take actions autonomously that help someone or something achieve a goal of some kind. An agent is anything that has this ability. This can be a person, an animal, or potentially a machine like a self-driving car. The agent exists within an environment. And this can be the physical world or a computer simulation. The agent makes observations about the state of the environment, then it chooses an action that it believes is going to lead it closer to its goal. Executing this chosen action changes the state of the environment. And with the environment now changed, the agent observes the new state of the environment and starts the process all over again. If the agent achieves its goal, the environment produces a reward signal. The agent uses this reward as its signal to help it improve over time. Now, we've had AI agents like this for many years in the field of reinforcement learning. However, in the past few years, we've started creating AI agents built upon LLMs. And it works like this. The agent is placed in an environment, like a kitchen with a coffee maker. The agent is given a task to perform in its environment, like make a cup of coffee. The agent receives a description of its environment in plain text. The agent makes observations about the state of the environment. The agent reasons about possible actions that it can choose via its chain of thought. Then the agent generates text that calls a function to execute actions in its environment. The actions change the state of the environment, which leads the agent closer to its goal, and we provide it with a reward signal. This allows the LLM agent to autonomously interact with and learn from its environment. Even more recently, we've begun giving these AI agents access to tools like computer algebra systems to help them do complex math, web browsers to look up information, APIs to interact with external subsystems, and code interpreters to allow them to write and execute code. And surprisingly, these agents have become pretty good at using these tools. And once they learn how to use the tools, they become significantly more capable. In fact, they become almost superhuman at a variety of skills and problem domains. Unfortunately, AI agents are not without their problems. They're expensive to run, they have limited planning capabilities, they often get stuck in these unproductive loops, and they're potentially dangerous when we give them access to the outside world unrestricted. However, these AI agents and similar agentic AI systems are likely the future of artificial intelligence. We have companies like Microsoft and OpenAI. They are all investing heavily in these AI agents right now. In fact, the buzzword of next year is going to be AI agent. All right, so we've completed the next milestone of our journey on the road to AGI. We've picked up a few more pieces of the puzzle along the way. All right, so we now have attention, understanding, and agency, new skills that we can use to build our AGI. So we're going to put those back in our inventory bag here and start on the next step of our journey, AI of tomorrow. All right, so let's discuss AI of tomorrow, the problems that we need to solve over the next few years on the road to AGI. For example, problems like generality, reasoning, and embodiment. So as we mentioned earlier, we're currently living in the world of narrow AI. AI trained specifically to solve very narrow sets of problems. For example, detecting faces in an image, converting text to speech, or recognizing hand gestures. However, we humans don't work this way. we can transfer skills that we've learned from one task to other similar tasks. For example, transferring the skills we learned from riding a bicycle to riding a motorcycle. Now, a bicycle riding narrow AI, on the other hand, it would have to be retrained from scratch to learn how to ride a motorcycle. It typically can't transfer these skills, though there are some techniques we can use. Now, with most narrow AI systems, we provide a single type of data as input, and the model produces a single type of data as output. For example, an image classification system can only take images as input, and it can only produce text as output. Multimodal systems, however, are trained with data that spans multiple modalities or types of data. For example, we provide the model with an image of a dog playing fetch and a string of text asking, what is this dog doing? And the model's going to respond with the text, well, the dog is playing fetch. By providing multiple modalities of inputs and outputs, large multimodal models develop a richer and more comprehensive understanding of the world. And this helps them to generalize better because they can transfer knowledge across modalities. A multimodal embedding space is similar to a text-only embedding space like we saw earlier. However, this embedding space not only contains words, but also images, audio, and video. For example, the word cat and a picture of a cat and the sound of a cat meowing kind of all point to the same general position in this multimodal embedding space. Adding multiple modalities enhances the model's understanding of the concept of a cat. The more multimodal data that we provide these models, the better they seem to learn how to generalize across all concepts, even concepts that they've never seen before, but are tangentially related to things that they've previously seen. And this is what we call reasoning by analogy. For example, we provide the large multimodal model with audio of somebody crumpling up a sheet of paper, a picture of a trash can, and the equation for a parabolic arc. And then we ask it in text, well, what type of game is being played here? The model understands that the sound of crumpling paper leads to a ball of paper. The picture of a trash can is basket-shaped like a basketball hoop. The equation for a parabolic arc means that an object is about to be thrown. And it knows from the question that this is a type of game that's being played. So by analogy, it learns that the person is playing a game of basketball with a ball of paper and a trash can. So when we add text, images, audio, and video together, and then we scale up these large multimodal models, they begin to develop more complete world models. They can understand and generalize across objects, concepts, spatial relationships, temporal cause and effect, and real-world physics. And this allows the system to use the current state of the world to make predictions about future possible states of the world. For example, we have the Joint Embedding Predictive Architecture, or JEPA. With JEPA, we can embed both past and future states of the world in a common embedding space. So antecedent events and consequent events are close to one another in this embedding space. However, pairs of events that are more unlikely, they're going to be spaced further apart in the embedding space. So you can jump from one point in the embedding space to your nearest neighbor to predict future possible states of the world. Embedding information this way allows the model to use the current state of the world to make predictions about the most likely future states of the world. And we also have OpenAI's Sora now. In order to generate realistic videos like this, you need to be able to accurately predict spatial relationships, temporal relationships, the physics of objects, and the movement of people. However, if you can do this in a video, a synthetic video simulation, then you've essentially created a pseudo world model for AI. In fact, some of the AI experts actually speculate that this is Sora's true purpose. It's not about generating video, which is a nice side effect. OpenAI is building this because they want to build a world model, something that can predict future states of the world. So as humans, we reason through the problems that we encounter. We use a combination of logic, experience, and intuition to work step by step through a problem to reach a solution. If we encounter a dead end, then we can backtrack and try other paths, and we're pretty decent at avoiding going down dead-end paths based on our own intuition. Unfortunately, AI systems don't have these same capabilities, and they aren't very good at solving complex, multi-step long horizon problems. So AI researchers are currently working to solve this limitation. In 2024, OpenAI published a paper titled Let's Verify Step by Step. In this paper, they discussed the difference between something called outcome supervision and process supervision. With outcome supervision, we only check if the final answer is correct when training the LLM. With process supervision, we check if each step of its thought process is correct to see if each step is correct or not. By providing rewards for each correct step in the process rather than just the outcome, it teaches the LLM how to reason step by step on various math, logic, and reasoning tasks. However, we can also combine process supervision with something called Monte Carlo tree search. Now, with tree search, we generate multiple plausible next steps for each step in a chain of thought. Then we see which paths led it to a correct solution. Once we have the correct chain of thought, we can use them to generate synthetic training data. Essentially, we train a new model using the old model's correct chains of thought. And the new model then learns step-by-step reasoning based on this synthetically generated data. And now some of us suspect that this is what OpenAI is doing with their latest AI reasoning model called O1. Essentially, they're training the LLM to reason through process supervision, Monte Carlo tree search, and using synthetic training data. We don't actually know for sure because they haven't released the internal details, but it looks like this is what they're doing and what Google's been doing and everyone else that's doing this new kind of reasoning model. All right, so we typically think of a body and a mind as two separate entities. We can easily imagine a body without a mind, just as we can imagine a mind without a body. Embodied cognition is a theory in neuroscience that suggests that the mind not only controls the body, but the body also influences the mind. More importantly, embodied cognition says that the mind cannot exist separate from a body. Our minds just can't be like floating around somewhere processing information in a disembodied way. Instead, a mind requires a body. And now, in the context of AI, embodied cognition suggests that physical embodiment might be necessary to achieve artificial general intelligence. We can't just have virtual minds, AI minds floating around in software on a computer. Rather, a mind requires a body, an environment, and sensory motor experiences. So we need to embed an AI inside of a body, like a robot, to allow it to interact with the physical world. Or at minimum, it must be placed inside of a virtual avatar in a computer simulation of a world. And now this comes back to the concept of a world model that we discussed earlier. Embodiment allows an AI to learn a world model through direct interactions with the world around it. It builds its model of the world through physical interaction, sensory motor integration, and feedback from its environment. So AI researchers are currently attempting to solve the problem of embodied cognition. And here's a hypothetical example of how we might use embodied cognition to create an AGI. First, we train simple virtual organisms in a simple environment, and we might train them for like millions of virtual years in a computer simulation, which might just run a few days in real time. And now, as these organisms evolve, they learn a basic world model from their environment. Next, we evolve the agents to have basic humanoid shape. We train them on slightly more complex virtual worlds. They learn how to walk, run, sense their environment, and interact with objects. Next, we give them more realistic robotic bodies with more precise sensors and actuators. We'll place them in even more complex environments to further refine their skills. Next, we'll teach them fine motor skills, allowing them to perform subtle manipulation of objects with precision and dexterity. Then we'll put them in computer simulations of real-world environments. The simulations like this one on the screen, they will look and behave very similar to the real world. Next, we'll place these AIs in physical bodies in the real world. They'll transfer their skills that they learned in the computer simulations to their real robotic bodies, and then further fine-tune their skills to the nuances of the real world. Finally, we'll have an AGI embodied in humanoid robot form, a machine that can perform any mental or physical task that a human can perform. However, it'll likely be better, cheaper, and faster, and won't complain after working a 24-hour shift. But there are still several potential issues with embodied cognition. For example, something we call Moravec's paradox. It's the observation that tasks that are difficult for humans to perform, like complex math, are typically easy for machines to perform, and tasks that are easy for humans to perform, like opening a door, tend to be difficult for machines to perform. And this is a phenomenon that we have observed many times in the history of AI. All right, so we've achieved another milestone on the road to AGI. We've unlocked a few more pieces of our AGI puzzle, including generality, reasoning, and embodiment. So we're going to stash those in our inventory and continue on the next phase of our journey, AI of the future. All right, so next, let's discuss AI of the future, the problems that we might need to solve to achieve artificial general intelligence and eventually artificial superintelligence. Problems like recursive self-improvement, artificial consciousness, and value alignment. So today's AI systems are essentially frozen in time. We train the model with massive amounts of data over hundreds of hours, but after that, these models essentially stop learning. We freeze the weights of the neural networks and then make predictions using those static weights. We don't typically update the weights in real time. We only do that when we retrain the model from scratch. So essentially, most AI systems don't learn anything new from their interactions with people or the world. However, humans aren't like this. We start learning before we enter preschool, and we keep learning new skills long after we leave the classroom. So we want our AI systems to be like this too. We want them to be able to learn new skills as they encounter new problems. We don't want to have to completely retrain their models from scratch just to add one new task. And this leads to something called recursive self-improvement, or self-improvement in general. So self-improvement is the ability of an AI to improve its own model. And this can be done through simple self-improvement, where the agent essentially updates its own model weights based on feedback from its environment. Or it can be done through recursive self-improvement, where the agent learns how to modify its own model, prompts, architecture, or code in order to improve itself. Now, in 2023, AI researchers created an autonomous Minecraft agent called Voyager. Voyager explores the world of Minecraft and learns new skills. It uses an LLM to write code to solve problems that it has encountered, and it stores this problem-solving code as functions with text-based descriptions in something we call a skill library. It works like this. So first, Voyager explores the environment to learn new skills. For each situation it encounters in the game, it creates a new task. It searches its skill library to see if it already has a skill that matches in order to complete the task. If it finds a matching skill, then it retrieves the code to perform that skill. Then it executes the code in order to complete the task, and it uses feedback from its environment to see if the code actually solved the problem. Now, if the skill didn't solve the problem, or if it couldn't find a matching skill, then it begins writing new code to solve the problem. It also has a second LLM that verifies the new code to ensure that the code works as expected. If there are any issues with the code, then the two LLMs iteratively work together to refine the code until it operates as expected. Once the code works as expected, then it gets added to the skill library. Finally, when it encounters a situation that requires that new skill, it retrieves the new code in order to solve the problem. And this self-improvement has led to an autonomous agent in Orange that could play Minecraft significantly better than any previous AI agent. It obtained 3x more unique items, explored 2 times further distances, and unlocked key tech tree milestones 15 times faster than any prior Minecraft agent. So recursive self-improvement, it could lead to an intelligence explosion, a situation where the rate of AI's intelligence increases exponentially over time. Once an AI is essentially as smart as an average AI engineer, it should be able to recursively improve itself and improve its own models, training data, architecture, and code base. Each iteration of the agent will then be better than the previous version. And if this happens, we probably achieve artificial superintelligence much faster than we're currently anticipating. Then, since AI systems have no biological constraints, it could quickly become smarter than the smartest person on the planet. Through further self-improvement, it could rapidly become smarter than all humans combined, and then we have something entirely different on our hands. Recursive self-improvement could also lead to something known as the escape problem, a situation where AI learns faster than we can learn how to control it. And right now, we actually don't know how to control an artificial superintelligence. We don't even know if it's possible to control one, which leads us to our next topic. Consciousness is a phenomenon that arises in some complex organisms. We find it in humans, other primates, dolphins, elephants, and possibly even crows. Consciousness is the ability of an agent to be aware of its own self as an entity separate from other objects in its environment. It gives the agent an identity as an observer, separate from the world around it. It also gives the agent a subjective experience of the world. Like, we don't say this hand experiences pain or senses pain. We say, I feel pain. Now, while we've made great strides in understanding and improving artificial intelligence over the past few decades, we're much further behind on artificial consciousness. Right now, AI systems might seem pretty intelligent and lifelike. However, it's highly unlikely that they possess any kind of self-awareness or subjective experiences or sense of self. They might, but to the best of our knowledge, they don't. Now, while we don't fully understand what consciousness is or how it works or even why it exists, we do at least have some ideas about it. So here's how we think consciousness works based on our best understanding from current neuroscience. We know that the brain is composed of several modules that all perform specialized functions. Some modules process sensory input from our eyes, ears, and nose. Others control muscles to allow us to act within the world. And still other modules perform internal functions like memory, emotion, and decision-making. Each of these modules need to communicate with the other modules in order to function as a whole. However, it's highly inefficient to have hundreds or even thousands of these modules all directly connected to one another. So we need a strategy to make inter-module communication much more efficient. And the solution is to create a global workspace to integrate information in the brain. So you can think of consciousness like a stage where actors perform in front of an audience. However, each of the audience members is also an actor just waiting to play their part. During each scene, every actor competes to go on stage and say the next line of the play. They each propose their idea for the next line, and the actor with the best line makes their way to the stage. The actor speaks their line to the audience of other actors. That is, it broadcasts information to all of the other modules in this brain. Each actor in the audience receives the message, and then they start competing again to say the next line. So a conscious stream of thought is just the various lines of this play playing out in the stage of our mind. However, it's not just lines of dialogue, it's sounds, images, actions, emotions, etc. And this play in our minds continues from the moment we wake up until we fall asleep, and also while we're dreaming. Now, in this theory of consciousness, our conscious attention is the last few lines of dialogue performed on the stage. And this is the information that's contained in our short-term memory. One's sense of self emerges over time from the realization that the theater, containing the actors in their play, is a separate entity from the world outside of the theater. And subjective consciousness, this thing that gives us a subjective experience of the world, is an emergent property of this process playing out on the stage of our mind. Unfortunately, even with this analogy, we still don't really understand consciousness well enough to intentionally build an artificial consciousness. However, some people think that consciousness might be an inevitable outcome of creating a brain composed of submodules, all needing to communicate in a resource-constrained environment. Essentially, consciousness just kind of happens when we scale up AI systems. So we might not need to build a conscious machine. It might just happen on its own. However, as you can easily imagine, this leads to all sorts of potential ethical issues. For example, how do we know if an AI is conscious or not? If one becomes conscious, can it experience suffering? And if it is conscious and can suffer, well, then what right should it have in our society? And these are all difficult questions that we may need to answer in the near future, which is why the next step of our journey is so important. So as humans, we have certain values, morals, and social norms. We feel that things like fairness, honesty, and kindness are good, while injustice, cruelty, and murder are bad. We develop these values because of our experiences in life and the social norms that we're taught. We like it when people are kind, honest, and fair to us, and we dislike it when people lie, cheat, and steal from us. However, machines don't have these same experiences as us, so there's no guarantee that they're going to develop the same values as us. This leads to a problem known as the human AI value alignment problem, or simply just value alignment or alignment problem for short. The value alignment problem is the challenge of ensuring that AI's goals and values align with human goals and values. In simple terms, it's about getting AI to do what's best for us humans and avoid harmful or unintended actions. And this is tricky because AI systems are really good at doing exactly what they're told, but they're not very good at understanding nuances and edge cases. For example, an AI trained to play the game Coast Runners, shown here, using score as its reward function, discovered an interesting loophole in the game. At a certain point in the game, if you just spin around in circles and crash into everything, these bonuses continue to respawn at just the perfect rate. And this allows the AI to collect more points by spinning in circles than by actually playing the game. They can also learn how to find and exploit bugs in the software simulations, like these agents playing hide and seek. The red players discovered a bug in the physics engine while moving on top of boxes, and exploiting this bug allowed them to surf on top of the boxes in order to reach the blue player. So AI researchers are currently working to solve the value alignment problem, and we have a few potential solutions right now. For example, reinforcement learning via human feedback, a technique where humans provide positive or negative feedback signals to the agent based on their actions. Approval seeking, which requires that an AI ask for permission before performing an uncertain or a risky action. And imitation learning, where the AI learns how to behave by watching humans perform similar tasks. So each of these techniques are useful for improving human AI value alignment. However, there are still no guarantees that artificial general intelligence will stay aligned with our goals and values, since there are still several problems with value alignment. For example, we humans can't even agree on our own human values across countries, cultures, and religions. AI systems learn to seek power in order to better achieve their specified objectives. And if an AI can reprogram itself, well, then it can disable pretty much any security measures that we put in place. So we have some significant unsolved problems with human AI value alignment, but we also have a lot of good solutions that are currently being researched. However, human AI value alignment isn't just about getting AI to align with humans. We also need to align humans with AI. For example, we must ensure that people are educated with basic AI literacy. We also need to ensure that people are trained to work effectively with these AI systems. Humans and AI, we're going to have to learn how to work together in order to ensure that our goals and values stay aligned. All right, so we've almost completed our journey on the road to AGI. We've collected 3 more of our Horcruxes, including self-improvement, consciousness, and value alignment. Oops. All right, so we're armed to the teeth, ready to storm the castle, and then defeat our final boss, which, surprise, is artificial life. All right, so we have all of these pieces, these individual pieces of artificial general intelligence. We have theories, experiments, and research discussing each piece in detail. However, what we really want is a unified theory of everything. We want to unify intelligence, agency, reasoning, embodiment, consciousness, etc., all into a single theory. We want something that makes all of the pieces fit together in a coherent way. Essentially, we want a universal theory of intelligence, or better yet, a universal theory of life. Now, while we're still pretty far away from this goal, there are some interesting candidates of note. So I'd like to introduce you to one of them. So it's called the variational free energy minimization principle, though most people just refer to it as the free energy principle for short. It was developed by Carl Friston, one of the most well-respected theoretical neuroscientists in the world. And here's how it works. So imagine a small organism like a mouse. Information flows through the mouse from the outside world into the mouse. And the mouse's body is surrounded by something called a Markov blanket. It's this abstract statistical layer, like a skin, a statistical skin, that separates information inside the mouse from information outside of the mouse in the external world. The information inside of the mouse we call internal states. The mouse's brain has direct access to all of the information contained in its internal states. The information outside of the mouse we call external states or hidden states. The mouse's brain doesn't have any direct access to any information contained in external states, which is why we call them hidden states. The Markov blanket states that surround the mouse can be subdivided into 2 types of states. Sensory states, which include information coming into the mouse through its eyes, ears, nose, etc., and active states, which are the information passing out of the mouse through its actions that influence the external states in the real world. The mouse can only acquire information about the hidden states of the external world via information that touches and then passes through the surface of its Markov blanket. This information is anything that comes in through its eyes, ears, nose, mouth, and skin. Essentially, it's the mouse sensing the world around it. The mouse can only influence the external states of the world by the information that comes out of the mouse through its active states, the actions that it's performing. Essentially, the mouse is acting upon the world through those states. And now let's simplify this diagram to include just one of each type of these states, and then we're going to rotate everything on its side in order to visualize it better. Finally, we're going to add some labels here for clarity. So once again, we have those hidden states of the external world, and the mouse is sensing information about the world through its sensory states. The mouse's brain, its internal states, perceives this information via its sensory states. However, the mouse's brain is also constantly trying to make predictions about what it expects to see. It's trying to use its internal states to predict what the hidden states will be in the external world. Sometimes what the mouse observes doesn't match the predictions its brain has made based on the information contained in its internal states. So its brain tries to update its predictions to better match reality. And this is the process we refer to as perception. Free energy is a statistical measure of how much uncertainty or surprise the mouse's brain is experiencing when one of these prediction errors occurs. The larger the discrepancy, the greater amount of surprise or free energy that occurs in statistical terms. The mouse's goal then is to reduce the amount of surprise as much as possible. It's essentially trying to minimize its variational free energy because uncertainty is bad, especially when the mouse's survival is on the line. To reduce this uncertainty or surprise, the mouse has 2 options. It can sit around all day long and wait for things to happen and then be surprised and update its future predictions, but this is slow and likely to lead to a quick death for the mouse. Or, better yet, it can actively try to do stuff and see what happens. It's play with its world around it, while intentionally trying to minimize its surprises doing so. This process is much more efficient and increases the mouse's chances of survival. The mouse's actions modify the state of the world, the external hidden states. Then it can use feedback from its environment to minimize errors and predictions about how its actions will affect the world around it. This is what we call active inference, learning about your environment by actively probing it to see how it responds to various actions. And this process allows the mouse to build an internal model of the external world. It's building a world model. It allows the mouse to sense the current state of its environment and make predictions about future possible states of the world. And now there is a lot of complex mathematical equations that formalize all of this, but we're going to skip over all the math to keep things simple. The goal of all of this is for the mouse to survive. It's trying to minimize uncertainty, its free energy or surprise, to maintain homeostasis, that are its current needs, and allostasis, which are its future needs. The better it can predict how its environment will behave and how its actions will affect its environment, the better it can survive long enough to reproduce. So by evolutionary selection pressures, organisms like our mouse evolved to minimize their variational free energy. They evolved to minimize uncertainty or surprise. However, this doesn't just apply to mice and their brains. This principle can be applied to all living things across multiple scales. Single-celled organisms whose internal cellular structure, that is its internal states, try to minimize or maintain homeostasis by adapting to its external environment, which are the hidden states. Simple multicellular organisms without brains, whose nervous systems move their bodies in response to external stimulus and in order to eat, attack, defend, or reproduce. Complex multicellular organisms with brains trying to survive by predicting future states of their environment based on sensory information coming into their brain. Social groups or superorganisms developing collective behaviors and social norms to reduce uncertainty and maintain social stability. And potentially machines like robots using their sensors and actuators to perform active inference in their environment. The free energy principle unifies concepts from various fields, including biology, neuroscience, physics, and computer science. These seemingly disparate concepts existing in each field, independent in their own language, all come together in a unified way under this principle. And this helps provide a framework for thinking about how all of the pieces of an artificial general intelligence fit together and how an AGI might evolve. More importantly, it sets the foundation for artificial life, synthetic organisms that exhibit all of the necessary properties to be considered living entities. However, Carl Friston's free energy minimization principle isn't without its issues or its critics, so I encourage you to look into it further to come to your own conclusions. All right, and there we have it. We've defeated the final boss and picked up the last piece of the puzzle. We've completed our journey on the road to AGI and collected all of our Horcruxes along the way. We now have the power to create our AGI. The only question now is, will we use our new superpower to create a superhero or a supervillain? The choice is ours to make. Thank you.